about Corsair, our in-memory computing solution for generative AI inference. When we discussed this talk with Mark asked us not to keep it less salesy. So that's what we have tried, and we have brought in like more all the folks from the engineering team. We have Satyam from the architecture team, and then Uttam, Akhil, and myself from the software team. So yeah, let's dive right into it. Satyam, if you can move to the next slide. Yeah. So here's today's agenda. We'll begin with our motivation for Corsair and outline the high-level benefits it offers right out the door. Next, we'll do a deep dive into the architecture, introduce the digital in-memory computing paradigm, and then show how it seamlessly scales to an entire rack and beyond. From there, we'll cover the software stack, all the parts involved in there, including talking about how we lower and map the different PyTorch models to our custom kernels, and the in-house inference serving engine, which we have built to meet the stringent requirements for a low latency batch inference. Uh, yeah. Then, Satyam, next slide, please. Thanks. Yeah, so this graph more or less captures the motivation for the in-memory computing paradigm. Like as you can see towards the left, like there have been times in the past when a new application has warranted a radically new computing paradigm, right? So if you look at the point where it shows graphics, you would see that like that was more or less the time when they started becoming the more dominant workload. And around that time, there was this advent of GPUs that enabled us to see the significant step up in performance when compared to the CPUs, which were the device of choice then, right? Obviously, we were all happy with what CPUs were offering. But when we had GPUs available at that time, the scale and imagination just exponentially increased. Now, similarly, as you move towards the right, AI happened, right? With similar underlying operations from the graphics world, we saw that GPUs have proven to be the device of choice as they've allowed us to train even larger and larger models. So essentially, like in one word, GPUs have bought us GPTs, right? So today they remain essential as like because the token level throughput, which has been powering the training of all these generative AI workloads, and also all the AGI related work that is happening behind the scenes. But as you now move towards the extreme right, you would see that like generative AI, more like the inference side of things have started to become more and more dominant. There has been this advent of like test time scaling, all the advanced reasoning kind of methodologies that have been developed, and also the push towards AGI where you're allowing the model to think longer and longer. We believe that inference is now becoming a more dominant use case, and this is where like this is what is our motivation for Corsair. So, and our talk is centered entirely around these aspects. So, Satyam, if you can move to the next slide. Yeah, and this slide overall captures the high-level system architecture for Corsair. So, on the left, it talks about the architectural advancements which we have. Like it gives us enormous memory bandwidth because of the extremely large on-chip memory we have. Along with that, we have this different kinds of interconnects, the die-to-die interconnect and the PCI connections that allows us to scale to a card and beyond. Then the in-memory compute, along with the native support for MX scaling like formats, that gives us high tops as well as allows us to do inference without any significant loss in accuracy. And then to wrap it up all, we have the software stack that allows us to write all the custom kernels which we'll be talking about, and the inference engine which we have built for serving these low latency workloads. And from like I think from here, like as we go towards the next slide, Satyam will talk about the architecture. So Satyam, feel free to take over.
Okay, thank you, Gaurav. Thank you everyone for joining. And before we start looking at and start appreciating the architectural choices behind Corsair, it might be good to step back and get a motivation for the problem. So let's scoot back all the way over to a term that many of you would have heard. It's called the memory wall. But what does that actually mean? It's a term that has been around for a while and that basically describes the growing disparity between the growth of computing tops and the related peripheral technologies such as memory bandwidth and interconnect bandwidth. So on this graph that came out last year, it shows the steady exponential growth in the computing tops in the dominant or the latest computing technology of the year. Whereas on the bottom of this graph, you see the technology, the memory technology is also growing, but the gap between the two curves is growing even bigger every year. Similarly, for the interconnects, whether you are looking at PCIe or NVLink or related technology, it's also growing every year. It's also growing exponentially, but the gap compared to computing tops is still pretty significant and even getting bigger. Now, that alone may not be a problem, but you have to see it with something else. And to understand that, let's define another term. It's called AI, but it's a different kind of AI. It's called arithmetic intensity. And it's a quantifying measure of how much a workload requires in terms of computational flops versus the amount of memory transfers it needs to perform those computations. And a, a workload that has a high arithmetic intensity would utilize a small amount of data that is loaded or moved around to perform a large number of computations, whereas an application which has low arithmetic intensity will spend more time loading and storing the data and doing less computations on it. These two things, if a workload has low arithmetic intensity and the fact that we are looking at a growing chasm between the compute throughput and bandwidth capacities, this becomes the factor that affects user experience. And the further away the memory is, the more time we will end up spending in waiting for the data so that the compute is able to perform its work. To further understand, I won't go into the details of how LLM decoding works for this audience. Suffice to say that we are more interested in the decoding phase of LLM inference. And there are a handful of signature attributes of this stage. One is that the whole process is extremely sequential. It's embarrassingly sequential, if there is such a term. And even within each of those sequential iterations for processing a single token, the key operations are vector matrix multiplications, unlike matrix matrix multiplications in the prefill phase. Now, the combination of these two very key attributes makes LLM decoding or token generation very low arithmetic intensity. We are extremely memory bound. And in order to manage the complexity of these attributes, there are a few choices that um, the LLM infrastructure typically makes. One is you can pay more. You can get a more advanced infrastructure so that you can serve your customers. The other is you can trim down the number of tokens that you're processing, but that, of course, has implications on the quality. Or you can just decide that you have what you have, and if it takes longer, it takes longer. Neither of these are really good answers to the problem. What we would like to have is reasonable cost, no compromises in terms of output token quality or length, and we don't want to wait as long. And these are metrics that have significant user experience impacts. And to put it in a more quantitative terms, let's define a few metrics as well. So the metrics of importance when evaluating the effectiveness of an LLM serving inference, there are two and two other related ones. The first is called TEFT or TTFT, time to first token. It is how quickly after user submits a query, they start receiving an answer. And if you think about it, this is largely coming from how quickly can you process the prompt or the prefill and get into the token generation phase. And the second is TPOT or time per output token. This happens during decode, during every token generation. This is how much time it takes for any given user in a system to obtain a token output. And related to that, when you put the two of these together, there is the overall latency, how long a user would see the output generation happening after they submit a query till they receive the final token. That's the overall latency. And throughput is at a system level, if you have multiple users, what is the total number of tokens being generated per unit of time by the inference instance across all the users and their queries. So we'll keep that in mind and keep referring back to these as we go through the material next. Now, remember that we said decoding of LLMs is extremely memory bound. Now, there is a usual knob that people play with, which is batch size when it comes to increasing the arithmetic intensity. The idea being very simple. If you have a large amount of data to be reused, you would keep the weights nearby as much as possible and process more activations through it or more queries through it. Now, this works really well if you have a non-LLM workload. Uh, for example, the old CNNs or something similar. You increase the batch size, you keep the same weight stationary or in the near memory, and just process more activations or inputs through it. And that way, you can exploit the locality, and consequently, you control the amount of data movement that needs to happen. The challenge is it doesn't really work for LLM inference. And why? The core reason for that is the KV cache. With increasing batch sizes, we also have to account for the fact that we have to maintain a larger KV cache, and that requires storage, and that also requires data movement. So one could think, compared to the overall size of these 70 or 100 billion parameters models, is KV cache significant? Well, it turns out it is very significant. Let's take a moment to digest the curve on this chart. Uh, the bottom three curves show the native arithmetic intensity of some of the common models, llamas and mistrals, for a reasonably moderate context size of 4K tokens. It is evident that on the x-axis, as you go towards a higher batch, the cumulative effect of KV cache starts to dominate. Up to a point, initially at small batches, you see a linear increase in the arithmetic intensity, which means they will become more and more compute bound. But after a while, you stop seeing any benefit at all. You can keep batching, you will incur higher latency, but nothing really changes as far as the throughput is concerned. So this is where the knee of the arithmetic intensity curve happens for the native workloads. Now, why is that important? If you also see, there are three other curves, the horizontal lines, which show where the arithmetic intensity of the accelerators are. And the idea being that if these two curves intersect, the workload arithmetic intensity and the accelerator arithmetic intensity, you have a chance to saturate the compute on that architecture. If they don't, for example, the Hopper or the derivative L40S, there is no chance that you can saturate the compute on that particular architecture by going to any batch imaginable. Whereas for something different, and we'll go into the details very shortly, for a different architecture, which we'll talk about now, there is a much lower arithmetic intensity curve, and it falls very much in the reasonable range of batch sizes. In fact, if you see, even at a batch size of 10 to 100, these curves intersect the Corsair native arithmetic intensity. And that means we can completely saturate the computational resources on Corsair without going to crazy batches. So thinking about that for a second, this requires something fundamental, something which is a paradigm shift. We really have to think about a way that we don't have to go to HBM at all. You load your model parameters once and forget about HBM after that. That is what is needed in order to accomplish the needs of LLM decoding today. So on the left-hand side is a more traditional GPU-like architecture where you have the standard HBM going through 8 to 10 terabytes per second interface, and you have the computing units which are operating at a certain compute throughput. This, as we saw, is going to be limited by how much bandwidth you can sustain from this interface, the HBM to compute interface. Whereas on the right-hand side, the promise of in-memory computing and near-memory storage is that you don't have to worry about the bottleneck being 8 terabytes per second because the data is available right where the compute is. So this is what the promise of the Corsair architecture is. So let's take a closer look. Looking top to bottom, this is a tiny picture of an actual PCI card, the Corsair silicon. And what you see in the middle is one of these two multi-chip modules, MCMs, and each of those MCMs contains 4 chiplets. So if you look closely, you will see these tiny rectangles inside of these. So this is an actual deleted MCM. So uh, the boundaries that you see are on the silicon. So these are slices and quads, as we will talk about. So each chiplet is further divided hierarchically into something called quads, and quad becomes a unit of independent programmability. And for this audience, we'll go quite a bit into details of what that means. Inside of a quad, we have 4 slices. Each slice contains a certain amount of memory and the computational core, which we'll show in a minute. Through a combination of chiplets, we are able and interconnect technologies, we are able to accomplish several things. First is we can scale quite a bit. We're not limited by reticle sizes. We can control the cost because it's much better yields that we can get with chiplets. We can get all the connectivity we want within a package or even between packages. And because we are aggregating the resources across chiplets, we can get high capacity as well as high bandwidth across all of them. And this is going to be key as we start looking at the performance characteristics of this architecture. Next, this is the detailed view of the Corsair chiplet, a single chiplet. And as mentioned earlier, inside of a chiplet, we have 4 quads. Each quad is an independent unit of computation. It has its own firmware, it has its own graph to execute, and it manages about 50 TOPS of compute inside of that. A quad consists of slices that contains the Apollo cores and the SRAM, the near memory, which is used for staging of waits and activations. I'll go over to Apollo core because that is the computational unit of all math operations. And here is where I apologize for a little bit of blurred image, but in the middle, this blue rectangles, these are the in-memory computing arrays. You can think of as the equivalents of tensor cores, but these are based on in-memory computing technology, where we stream in the activations and keep the weights stationary into the memory. And the act of loading the activation, streaming the activations through the memory multiplies them and we can accumulate them. And it's all done using complete digital circuitry, something that we've designed in-house, so that we don't have to worry about analog operations and instability from temperature and environmental effects. And we can use all of the goodness of quantization that we've developed as a community in the digital world. So all of that is available. In addition, as Gaurav mentioned earlier, we utilize the MX microscaling block formats. And that has the benefit of getting integer-like efficiency of operations, while we maintain the accuracy that we would get with regular floating points. So that is pretty cool. And in order to make it completely seamless, we also have a whole bunch of hardware-based converters that allow seamless data type to transfer between block floating points and standard floating points. The standard floating points being used for vector operations, the SIMD processing, such as softmax, layer norms, element-wise, and so on. So this is the view of an individual Apollo core. So you put a bunch of these together into a slice. You put a bunch of the slices into a quad. You put a bunch of quads into a chiplet, and that's the hierarchy. Now, another important thing that this group will appreciate, I'm sure, is how is work actually orchestrated on this processor, on this architecture. So here also, we've innovated not only on the data plane and the computational resources, but also put a lot of thought into ensuring that our control plane doesn't become a bottleneck. In fact, we went ahead and created some innovative data structures, both in hardware and software, So it's a mirroring. We have a unique representation of work called a hierarchical queue, and this is mirrored in the hardware. The idea being that we want to maximize the concurrency because we're not dealing with a GPU like traditional thread-based architecture. We can dispatch work across as many resources as we need. So there are parallel transfers, parallel operations, computations, reductions happening at the same time. And the way to represent that is through the concurrent queues, which captures both the concurrent nature of operations, um, which symbolically is represented here along the x-axis. Everything along the x-axis is concurrent, whereas everything which is in along the vertical direction are sequentialized. So you can capture the concurrent and serial dependencies of workloads using this representation. And there is a built-in hardware support, which we call dispatch engine, that manages these decisions. So the decisions are made by the kernel authors and the compiler, and the hardware ensures that these are followed and orchestrated with minimal overhead. Another thing which is pretty cool is because of our unique hardware software co-design, we are able to support the auto regression in hardware. So imagine that you have a graph whose context size is constantly increasing, but you never have to recompile it. You compile that graph once, deliver it to the hardware, and the hardware independently handles the increasing context size. So that's an attribute of how we define our instruction and the control plane. Okay, now switching gears a bit. It's interesting to think about a chiplet and the design of the chip, but AI is not a chip problem alone. AI is a scale problem. AI inferences requires scale out and scale up, and we have to handle that the same way that we handle our co-design for an individual chip. Um, a few things before we go into the topologies is that there are different attributes of different phases of computation. During prompt processing, if we are performing collective operations, these are typically very large tensors, and these require very high bandwidth. Whereas during token phase, you're basically sending 1 by D model, tiny tensors, kilobytes, and these require connectivity and low latencies. It's a careful design choice to come up with the right topologies that can be scaled while not incurring an enormous cost in terms of the wiring and the connectivity. So we take this approach of providing an all-to-all, fully connected topology across 16 chiplets in hardware. And we also provide a similar library of collective operations that exploits this all-to-all connectivity using one-hop trees. So that's our extension of hardware-software co-design, taking it from chip design to system-level design. So our tensor parallel unit, and I'll show a picture in a second, is optimized for both small transfers because we have high all-to-all connectivity, as well as for large transfers because we're not compromising on the memory bandwidth or the interconnect bandwidth in between the chiplets as well. It increases further. It doesn't stay limited to 16 chiplets. We can go to even rack levels, and we'll talk about that in a second again, using pipeline parallelism. And another unique aspect of our hardware architecture is that we tend to prioritize gather-based operations, collective operations, over reduce-based operations. There are many reasons to doing it. The obvious being that performing gathers can be done in a lower precision, and therefore it incurs a lower communication cost as opposed to reductions. And the second is that we have extensive support for multicasting in our architecture. So if you have to provide the activations from a previous column-wise sharded phase as activations to the next matmul, you can do a direct multicast and avoid a need for an explicit all gather. So that's the kind of optimizations that have been put into the hardware to support collective operations. So with that in mind, let's look at how the scaling happens. So this is, again, a schematic view of a multi-chiplet package. These are 4 chiplets, And these are connected in an all-to-all mesh using die-to-die links. So these are based on the bunch of wire specification, and these provide 128 gigabytes per second bidirectional across all the chiplets. And this is, again, it's very conducive to creating a one-hop tree between the 4 chiplets. And that extends to a physical PCI card where you place 2 of these. Each of these 4 chiplet groups are all-to-all connected. And you have a PCI line going between the 2 packages, between the 2 MCMs, that provides an all-to-all connectivity between the 8 chiplets. Now, this was scaling up from a chiplet to multiple chiplets. We can also take it one step further and provide the connectivity between 16 chiplets between 2 cards. And we do that using our what we call a DMX bridge. Think of it as an equivalent of an NVLink bridge, but this is a standard PCI-based connector, a passive connector, that is placed on top of 2 adjacent cards, and that provides these purple lines that are connecting the chiplets across the 2 cards. So at this point, we've created a 16-chiplet all-to-all connected tensor parallel unit, which can support ultra-low latency collectives for sharded operations.
Satyam, I had a quick question. Like, I've seen, like, I mean, I'm not a computer architect, so please forgive my naive question, but like, I've seen, like, for example, when the B200s came out, like, people sort of were making fun of it. They're like, oh, like, you know, the chip goes twice as fast because you have twice as many chips on the like being sold and packaged as one. So could you sort of help me understand, like, how come the chiplet design became somewhat mainstream and what are the benefits? And is, like, my prior critique somewhat naive? I'd love to hear why that's the case.
Yes, great question. Why chiplets? So these individual chiplets are not small. These are 400 plus millimeters squared. These are huge by most standards. And if we make them any bigger, we are running into the reticle limits. And that affects yields. Some companies and some designers feel comfortable putting in solutions so that they can recover some of the lost yield. But we feel a more scalable way, and we see that happening across the industry, is to go with composable architectures. The idea being that you don't have to be limited to a single monolithic chip. You can compose them using nicely interfaced chiplets, with the benefit being that you could do heterogeneous scaling as well. There's nothing preventing us from putting in a compliant chiplet that serves a different purpose and interface it directly with the Corsair chiplets. So that kind of composability is another reason why the chiplet-based designs are seeing popularity. Plus, there is benefit in terms of the spacing, the cooling, um, how you deliver power to them, how they can be fit into a wide variety of form factors, because PCIs as well as OCP provide some mandated dimensions for the packages. So all of them becomes easier to manage when we have chiplets that can be played around with.
Got it. Thank you. That was a great answer.
Okay. So that was up to a tensor parallel unit of 16 chiplets. Beyond that, we can go through a PCI fabric to scale up further within a server. So here, for example, this is showing a dual socket CPU with a PCI switch that is connecting to multiple such PCI Corsair cards, dual cards. Each of the cards has a by 16 link going into the switch. And these are all still all-to-all connected. It's just that these are not going to be for one-hop tree-based collectives. These are primarily going to be used for pipeline-based communication. And now, why stop at a single server when we can take it further? So the last thing that I wanted to flash is an Ethernet-based solution that can be used to extend the scaling from a single server, not just to a rack, but to a cluster of racks. So you do it using our own custom designed network interface card that is built using TCP-based streaming. It becomes a natural extension of the PCI-based transfers that we have created in between inside a card as well as inside a server. And the NIC does the transparent porting of PCI over Ethernet using using more traditional spine leaf kind of switching infrastructure. So that allows us to go to hundreds or thousands of such Corsair cards to serve the largest of the models that we want to serve. Now, before I hand off, the audience, I'm sure, would be wondering, how do you actually program that thing? That looks complex. Well, there's some good news. All of that is abstracted away by these 15 instructions, or just a small 15 to 20 instruction set. You can take any workload, including long distance communication, including collectives, including synchronization. Everything can be expressed using a really tiny instruction set. The core elements of which are shown here, and a very small toy example of a graph is shown here. So these specify fetching things from DDR, moving things from SRAM into registers, performing an operation using IMCs, moving data back into SRAM, and further flushing it back into DRAM. I'm sure this is something that the audience would like to learn more about, and I would hand it off now to Uttam to talk about the software and how kernels are actually written using this instruction set.
Right. Thank you, Satyam. All right. So I'll be talking about the software stack that enables all of the acceleration of these large language models that Satyam talked about. All right, so this shows an architecture diagram of our software stack. There are two main pieces that we'll be talking about today, the lowering stack and the execution stack. I'll be focusing on the lowering stack, and later in the presentation, my colleague Akhil will focus on the execution stack. So the lowering stack consists of a couple of different pieces. Right at the top, you see a piece that we call the model factory. The model factory is where we take models, models that have been released by the open source community, the transformers package, etc., and modify it a bit to work on our hardware. So some of the typical modifications that we might do include introducing of collectives to support communication across multiple cards, introduction of annotations of custom operations, etc. Once we have a model in the model factory, we export it from Python to FXIR, and then we put it through the rest of our lowering stack. So at the top of our lowering stack are the quantization tools, and these quantization tools introduce into the graph various nodes which help us to quantize the model into some of the numeric formats that we talked about, chiefly the microscaling formats. And once we have that quantization done, there are two paths by which we can lower a model to get it to run on our hardware. The first is through a graph compiler, which is an MLIR-based compiler, which takes in on the front end an FXIR graph and lowers it through an MLIR-based proprietary intermediate representation, all the way down to the ISA that Satyam just talked about. In that process, it can incorporate small handwritten pieces of code at a fairly low level that we call kernels, and use them to produce the ISA output. A second method of lowering is what we call the model builder approach, where we would take these kernels and stitch them together to form a workload. This talk is going to chiefly focus on the kernels and to a certain degree on the model builder approach. All right. So I talked about a kernel. So what is a kernel? A kernel is a method typically written in Python, which converts an operation, the operations that we're all familiar with as part of large language models, gems, convolutions, softmaxes, things like that, and converts it to a directed acyclic graph of machine ISA instructions, the same ISA instructions that we showed a few slides ago. An operation can vary in complexity. So it could be as simple as the operations we know, gems, convolutions, things like that, that we call fine-grained. But it could even be what we call medium-grained operations. And so these are connected groups of these smaller operations. So things like attention heads, decoders for models such as Llama, or it could even be what we call coarse-grained operations, which are decoders, for example, decoders integrated to form a full graph, such as a token graph or a prompt graph. Now, when we talk about these kernels, a few things to keep in mind is when we run workloads, as we described in the architecture part, we have built an in-memory compute architecture. And what that means is we have an extensive amount of SRAM on the chip. And to run and deliver the kind of performance that people expect from a large language model, we typically use SRAM resident graphs. So we try to keep the graph completely in SRAM and execute completely from SRAM. So this is in contrast to typical GPU type architectures where weights are brought in from HBM. And it differs a little bit also in the sense that it's a graph execution. The graph is completely kept on SRAM and executed on the chip. In contrast to a typical kernel execution with a GPU, which follows an eager execution type of architecture. So I'm going to focus on kernels, and I'm going to talk about kernels with the assumption that everything that's needed for the kernel operation, both the activations and the weights and the KV cache, are resident on the card, either in the DRAM or the SRAM. The transfer of weights from a host to the card, DRAM, will be talked about as part of the next section, which it's part of the what we call our Aviator runtime, and so we'll talk about that in the next few slides. And so we built this method of converting gems by a developer into these low-level directed acyclic graphs of ICE instructions. So what's the motivation behind this? What we want to do with these kernels is provide the developer with the ability to exploit every single feature of the hardware that you can use to maximize performance. And those include various things like allocation of data at a very fine grain across the SRAM, across the entire chiplet, across the entire package, as well as allowing the user to control the implementation of various mechanisms such as pipelining, parallelization, spatially, fusion of operations, overlapping of compute and communication, control them at a very fine grain and exploit all the hardware that we have, all the hardware features that we have to deliver this kind of performance. All right, so a kernel, I mentioned it's a handwritten piece of code, typically in Python, that converts from an operation to a directed acyclic graph of ICE instructions. It essentially consists of two parts. One is the directed acyclic graph generation, and the second part after that is what we call task scheduling. The code on the right-hand side shows a typical, what we call a core kernel. And as you can see, the core kernel takes as inputs a set of resources on which the core kernel is supposed to execute. So for example, in this case, we see that the arguments to the init function are the exact quad and core on which this kernel will run. So if you remember from the architecture discussion, a chiplet is divided into quads, and quads are our major unit of compute execution. A single graph runs on a single quad, it gets dispatched and executed. And so when you're writing a kernel, you specify the particular quad on which the kernel is set to run. And you can specify it at a much finer granularity, such as a slice. A quad is composed of slices, or an even finer granularity, a core, which is a component of a slice. In addition, when you run the operation, you pass input tensors, and the inputs to a kernel consist of these computation resources where the kernel will run, and also the memory locations of the inputs and the outputs. And so these are at a very fine grain. We specify where the input and output tensors lie. So we specify the exact location on SRAM where the tensor lies. And once you execute the core kernel, or once you run the multiply function, what happens, and you can see here, there is a looping over the m, k, and n dimensions of the tensors. And it loops through these, and the activations. So you can see here that we are moving activations into compute units, and we're adding the various instructions that constitute the graph, the various instructions that constitute what needs to be done for that operation into the graph. Similarly, we're moving the weights into the compute units, and we are adding the instruction for doing the weight transfer to the graph. And so the graph is being constructed here as the multiply unit is as the multiply function is being executed. And once that directed acyclic graph is...
I'm sorry, Vitam, I just had a quick question on the previous slide. So first off, like I really like Pythonic kernel DSLs, and they're great. There's like a lot of interesting ones. At least like I'm trying to understand the programming model from your comments. Like it seems that like this is lower level than something like Trident because you are explicitly modeling data movement. And I'm sort of curious, like I was wondering if you have any samples of like what this looks like. Like what does, for example, something like move activations into compute units actually look like in real code?
Yeah. So a couple of slides down, we have a sample of code from the perspective of a user. So it's the kind of code that will go into our model builder, and so that will show you how a user would use this kernel. So where he would allocate the various tensors and how he would call the kernel. So maybe just hold off until then, and you can see the code side by side, and then we can talk about it. But I think you rightly pointed out that it's much more lower level than Triton. And as we build these kernels, once you'll see in the next couple of slides, we talk a bit about the division of responsibilities between the kernels and then the workload writers. And then the workload writers, so our intention at some point in time is to even abstract that a little more. So that's what we do.
Yeah, and this was sort of the leading part of my question, which was like I worked very briefly at GraphCore before I joined Meta. And like one of my observations there was that like basically because you sort of had this like giant giant grid of SRAM, like people didn't really know how to program it, so you had a very sophisticated compiler. But the problem with that approach is that like for people trying to enable a new model, they're bottlenecked by engineers that work at the hardware vendor. It sounds like y'all took a different approach, so I'm very eager to learn more about that part. Hopefully it comes up in future slides as well.
Yeah. All right. So I mentioned the first part of the kernels is the directed acyclic graph generation. Now, once the directed acyclic graph is generated, the next step is to convert that directed acyclic graph into a set of task groups which get allocated to queues. So earlier in the presentation, we talked a bit about the dispatch engine, which is a piece of hardware that is present in every single quad of the chip, which dispatches instructions. And because we have so much parallelism on the chip in terms of spatially distributed memory as well as compute units, we want to be able to dispatch all of these instructions in parallel, where parallelism can be applied, and in series where there is a serial, where something has to be executed in series. And so the next step of this is to take that directed acyclic graph and then map it into these task groups that can be fed into the dispatch engine. So this part of the kernel generation is pretty much automated. So once you have the directed acyclic graph, the directed acyclic graph represents dependencies, both resource dependencies as well as data dependencies. And from that directed acyclic graph, it's fairly easy in an automated way to extract the parallelism that you can apply to this directed acyclic graph and ensure that where parallelism is required, we execute these operations across different cores. And so overall, when we convert this directed acyclic graph into these tasks, the goal is to achieve high utilization. And by mapping this directed acyclic graph onto these task groups, the goal is to achieve high utilization through pipelining, overlap communication, and in addition to do certain things that the hardware provides. So the hardware provides us methods by which we can minimize the control path overhead. through various things like what we call instruction multicast, where if particular operations are mapped to this to parallel compute units, and tensors are mapped to corresponding arguments in memory, they can be executed in parallel, and also to minimize data path overhead. So in this stage, we can coalesce various DMA transfers and ensure that the DMA transfers use minimum amount of overhead on the NOC. All right, so let me talk a bit about the division of responsibilities when you're writing a core kernel. The kernel itself takes up the responsibility of doing certain things, and the remaining part of the responsibility lies with the developer. So if you're following the model builder approach, a developer has to do these. Or the compiler. If you're integrating a kernel in with the compiler, then the compiler has to have enough features to be able to do this. And so the way we look at it is the model builder and the compiler does macro resource management, very high level resource management, and the kernel does micro resource management. So what do I mean by this? The programmer explicitly manages tensor allocation in DRAM in the main parts of the SRAM. So our SRAM has what we call activation SRAM as well as wait SRAM. And the user, the developer, manages the movement of data from this DRAM to the SRAM. On the other hand, the kernel manages the resources that are much more closer to the compute. So for example, when we want to do a matrix multiplication, we first have to move the activations into what we call input buffers, the weights into what we call weight buffers. And once the matrix multiplication is done, the output goes to the output buffer. And so the kernel manages all of that. And it's somewhat involved because this is the part where we have to be very careful in order to manage this well, in order to get the pipelining and extract all the compute that we can without leaving any bubbles in our pipeline. In addition, inside the kernel, while it's generating the code, it creates a set of dependencies. So within the kernel, the dependencies that are managed are chiefly resource dependencies, because we're moving things in and out of the input and output buffers. We have to be careful in order to ensure that, in order to avoid hazards. And so it's the kernel developer's responsibility to allocate resources and to make sure that when the resources are used, he avoids reading and writing hazards. On the other hand, the model builder or the developer who's building the kernel has the only dependency which he has to worry about are the data dependencies across kernels. So if one kernel wants to use the output of another kernel, then it's the responsibility of the developer to ensure that. And so the last thing that the kernel does is the ISA code generation. So the model builder developer deals with the interface that I spoke about, which is what are the resources that are used for a kernel, and then what are the tensors, and what are the memory locations of those tensors, and doesn't really need to worry about the ISA. But the kernel developer really needs to code this ISA up and ensure that the ISA that's developed, the ISA instruction that's executed, manages the IB and the OBs correctly without any conflicts. All right, so Mark, here's the code that I was talking about. So on the right hand side, you see the kernel code, which is it's the same code that I talked about. I mean, so you have a matrix multiplication. The resources, it takes as input the resources on which the kernel needs to run. And the multiply function takes as input two tensors, and those tensors have the memory locations where both the activations and the weights are located. We loop over the MK and N dimensions of the input and output tensors. We generate the code. We generate the ISA instructions, the GM to IB, stash to WB, the MATML and ISA instruction, and then the instructions that pull the results out. We generate them as a graph. And then we add the dependencies in there, and so the output is essentially the graph that can be lowered onto the chip. On the left-hand side, this is the model builder code. And so the model builder code, this is what a developer would have to write, or this is the code that a compiler essentially would have to generate. We have a tensor that's been allocated, a logical shape that's been specified, and a physical layout that has been specified. So where in physical memory, which bank and at what offset is this tensor placed? And so we have it for the input tensor, the activation tensor, the weight tensor, and the result tensor. And then you can see the rest of the code. So the rest of the code is what we do in order to generate the graph. So we instantiate the kernel, and we call the multiply operation. In this case, what we've done is we've called two multiply operations. The output of the first multiply operation is used as the input to the next multiply operation. And so we've created a graph here of two matrix multiplications back to back. And then we call the cogen. And so once the cogen is called, the output of that is a directed acyclic graph of ISA instructions with appropriate dependencies that cover data as well as resources. And it's essentially a form that can be put as input to the next step, which is the task scheduling step, where the individual ISA instructions are allocated and put into various queues. So Mark, I mean, any comments on this? Did this answer your question?
It certainly does, yes. One sort of specific question I had, I remember from Satyam's slides, he had a comment around how like you natively support like dynamic shapes. And I'm just trying to square that with the sort of you need to determine your graph beforehand programming model.
Yeah. So we'll talk a little bit about the dynamic shape. So I'm going to cover a couple more examples of this. And so we talk a little bit about the KV cache implementation. And so I'll talk a little bit about dynamic shapes when I do that.
So yeah, and I guess like maybe this is more a comment for after the talk, but if you have like a few examples of like full kernels, like basic ones, like even like ReLU, pointwise, norms, etc., I think people would really enjoy like checking those out in the server and trying to understand the programming model.
Okay, all right. All right, so this sort of shows internally what a kernel needs to do. We talked a bit about the compute units and then the input buffers, the output buffers, and the weight buffers, and the iteration through the MK and N dimensions. So when we're writing the tensor, we mentioned that we need to iterate through the MK and N dimensions, and so this shows the movement of activations from the input buffers, from the activation SRAM into the input buffers, and from the weight SRAM into the weight buffers, along with the compute. And because it's done in an iteration, what the kernel tries to do is to build a kind of a pipeline like you see on the right-hand side. And so this kind of a pipeline shows the various iterations. So on the first row, you see the first iteration. It's iterating through the K dimension, and you have the movement from the main memory into the input buffers and the weight buffers. The next time cycle has a matrix multiplication, and the third time cycle has the movement of the results from the output buffer into the main memory. And so you have this kind of a movement. You have this operating in multiple stages, and so this is the kind of pipeline that the kernel tries to build. Okay. And so also the kernel tries to do various things such as minimizing the data control path through the data path, the overhead of the data path through data multicast. And so at the end of the graph generation, the DMAs are all coalesced, as well as instruction merging. It takes advantage of the structure of the hardware and the placement of weights and activations to introduce things like multicasting of instructions to all of these compute units across the quad. All right, and so what we talked about was the matrix multiplication in the context of a single quad. Now, when you have to scale the matrix multiplication out, we need to scale it out. This diagram shows how we scale it out to a full chiplet, and it can be extended in terms of how we scale it out into a single package, into a single card. So essentially what we do is we take the weights and we partition the weights. We partition the weights and we can partition them either in a column parallel fashion, a row parallel fashion, and allocate them to the quads. And then the activations, we would appropriately multicast them to the individual quads. And then once the matrix multiplication is done, each quad has its own independent graph, which is triggered independently. The synchronization primitives that we showed in the list of ISA instructions are used to synchronize the individual quads. And once the quads complete, we introduce a collective using the memory transfer operations, and then the data can be collected. And so this is essentially how we would scale it out. And all of these would be written as separate core kernels, which would sequentially be stitched together to achieve this. All right. So how do we go from there to something much more complex? So this shows the code for a Llama 3 decoder kernel. And the way we build kernels essentially is hierarchical. We build various matrix multiplication kernels. We compose more complex kernels such as GQA kernels out of matrix multiplication kernels. And then out of these GQA and matrix multiplication kernels, we compose a decoder kernel, very similar to the structure that you would see when if you were to take a look at any model on Hugging Face or anywhere else. The key difference though is prior to stitching things together, we have to allocate places on the chip where constants would lie, such as the weight, the various weights, and we have to set up dependencies across the operations, which is what we do when we stitch the kernels together. And once we do all of that, we just call the cogen function, and then the cogen function essentially generates the graph for us. All right, and then this essentially was how a decoder is written, and then what we try to do is, since we are an SRAM resident architecture, we need to move this. We have to be able to scale this across multiple cards, and so our architecture consists of typically doing tensor parallelism across a full card or across two cards. And then doing a combination of, and then building the model through a combination of this kind of tensor parallelism and then pipeline parallelism across multiple of these TP units. So this shows how we would typically do this kind of division for a decoder. It shows the first decoder being sharded in a tensor parallel fashion across two cards, and a pipeline operation being introduced across the two tensor parallel stages. And of course, in between the two stages, we have to introduce the various collectives. And so as we talked earlier about the model factory and that being the place where we would introduce these collectives. So that's what we do. I mean, we take a look at the hardware, decide how we would like to parallelize either in a pipeline or tensor parallel fashion, and then in the model factory put those annotations and add those annotations. And once those annotations are in there, this is how we would structure the kernels to scale out.
So
right.
another question on this, like, so as far as like those high level APIs for things like collectives, like, does it look PyTorchy? Is it just like the PyTorch native calls? Is it like the lower level thing? Is it like more of a kernel language where you manually call these things? Yeah, like just help me understand how this works a bit more. Is it like a wrapper? Are you manually doing comms or not in your code?
Yeah, so in the kernel we are manually doing communication. So we showed a set of ISA instructions for transfer of tensors between various parts of the memory. What we call the activation memory, and so we would activation memory and wait memory. So we have ISA instructions to transfer tensors from various parts of the memory through a NOC throughout the chiplet. through our die-to-die communication interfaces between chiplets, and through PCIe between packages. And so the ISA covers all of those. So when we would want to write something like a all gather, for example, we would write it as a hierarchical set of all gathers where we would exchange data first between two packages on a card, say, and then exchange that data across the 4 chiplets within a package, and then within a chiplet. And so we would structure this all gather as sort of this hierarchy of three types of operations, and we would code it up in this ISA. And then we would provide that as a core kernel, just as the core kernels that you saw, just as the previous examples that you saw, with the slight exception that when you have to go across quads, and you have 2 sets of operations depending upon running on 2 different quads depending upon this collective, then you need a synchronization mechanism. And if you remember, in the list of ISA instructions, we had synchronization instructions, barriers that could be waited upon, and so those are used. What happens is, for example, in this decoder, let's say between the attention head and the projection matrix multiplication, we had an all gather. Then what would happen is, and this decoder is tensor parallel sharded across, let's say, 2 different packages. Then the 2 different packages would operate asynchronously until they came to the collective, where they would hit a barrier and pause. They would exchange data, and once they exchange data, the barrier would be released, and then they would progress with the rest of the decoder. So that's sort of how it would work.
Can I add something?
Sure, go ahead, Satyam.
Yeah. Mark, to your question, there is 2 flavors. One is what Uttam described is the low-level implementation of these collectives. So these are embedded into the graph. There is no invocation from the high level. But if you're talking about how do you provide introduction of a collective at a model level, that would look very PyTorchy at our model factory level. But we translate that through either the compiler path or through the kernel path. And eventually, there's no host-based call for collective. It gets embedded into the graph.
I guess like one thing that y'all didn't do, like that you kind of undersold, I felt, was like, because like presumably the model builder is Python, the kernel is Python, the graph is a string. All of this is like quite debuggable, it seems like to me, like where you can just like print the graph and like look at like what's going on, and that looks really cool, actually, for what it's worth.
Yeah, that's true. I mean, certainly the fact that we've built this in Python certainly helps. I mean, it helps with rapid development and also with rapid debugging. We can split the graph at any point that we want to, and execute parts of graphs. And then we have, I think I flashed a set of tools in the software stack. So we have a set of tools that allow us to probe memory at any point in time, take a look at that memory, and so debugging essentially becomes fairly easy. All right. So this is the third example. I'll talk a little bit about the GQA attention head that we've implemented with the KV cache. So with our KV cache, as I mentioned, we're an SRAM resident solution, and so the KV cache is fully SRAM resident, and so we have a static allocation of SRAM for both the K and the V caches, and we do this at kernel build time. So what the developer has to do is, once you're given a model, and the model has a certain set of parameters: the number of heads, the number of groups, D head, D model, context length, and batch size. Based on those parameters, it's easy to figure out what kind of a mapping you want for your KV cache. How many of the quads, for example, you want to spread the KV cache across. And the next slide will show you sort of how we do that. But based upon these inputs, a kernel developer would take a look at these inputs and decide what kind of a mapping he would want to use. Typically, what we do is we take the context length and shard that across our weight memories, and this enables us to extract a huge amount of parallelism during the operations, during the attention head matrix multiplications, the QKT and the XV matmos. As you pointed out, Mark, I mean, during the token generation phase, every token generation iteration has a dynamic shape that it needs to process. So the size of the vectors in the attention head matrix multiplication changes every single iteration. And to handle that, we have within our ISA a certain method by which we can change the parameters of an ISA instruction at runtime. So based upon the iteration, so whether it's the first iteration or the 10th iteration or the 20th iteration, we can rewrite an ISA instruction at runtime. And by doing so, we can modify the cache locations in the instruction stream that is used to do the attention head matrix multiplications. And so that's the way in which we do this dynamic shape handling. The way it's done is the kernel itself must add those special ISA fields, which are resolved at runtime, and the runtime, which we'll talk about in the next few slides, has to pass down into the kernel these iteration numbers. And once those iteration counts are passed, at runtime we can resolve this, and then we can dynamically generate the code that manages the KV cache. So this shows this slide shows a little bit about how we would do this mapping. So for example, in this slide, what we're showing is a case where we have a sufficient number of attention heads to map each attention head to a gang. A gang is just a synonym for a quad, but it is grouped attention. So the group itself would be shared across multiple gangs, and so the group is allocated across multiple gangs, and the head itself resides on a single gang, which means that any query that is restricted to a particular head must operate on KV cache entries across the other gangs. And the way we do that is initially, when the kernel starts off, each individual head has its own query. But what we do next is we do an all gather on all of the input queries, so that every single gang which has a head has all of the queries. And so now, given that the KV that the K cache is spread across all the gangs, we can do the operations on these queries, and the resulting vector would be spread across all of the gangs. And so the next step after the QKT is to do a softmax on the outputs of that QKT. And so since the input to the softmax is distributed across the individual gangs, you need to do the softmax in a distributed fashion. And so we do the softmax in roughly 3 stages. First, we do a local reduction, followed by an all gather of the results, and a final reduction. And then we do the element-wise part. And so this is essentially how you would structure the QKT matrix multiplication with a grouped query attention, where the group is spread across multiple gangs, and the heads reside on individual gangs. And so the XV operation is somewhat similar to this. So with the XV operation, the V cache is also spread across multiple gangs. However, because the reduction is done on the inner dimension, that's the sequence length, you don't need an all gather at the beginning of the XV kernel. Instead, you can because the query is available on each of the individual heads, you can directly do the matrix multiplication. But towards the end of the kernel, after you've completed the matrix multiplication, you need a reduction scatter, a reduced scatter, in order to collect the individual results and do the final reduction. All right. So we walked through three basic kernels: a basic matrix multiplication kernel, a decoder kernel, and then the GQA kernel. And so this shows how we we would build these individual operations, but these individual operations have to be stitched together to build a workload. And so we have two approaches to do that. The model builder approach essentially is an easy way of stitching together very large scale kernels. I mentioned we have three types of kernels: the fine grained, coarse grained, and the medium grained. A decoder kernel, for example, would be a medium-grained kernel. We would generate the graphs for the medium-grained kernels, such as decoders, which would run across the individual quads. And then we would stitch them together in the model builder, as simple as just taking the output of one kernel and making sure that it's fed in as the input of the next kernel. And so that's one way of generating our workloads. The second way I mentioned is the compiler. And then the compiler for simple workloads can do a complete automatic code generation of a workload. However, for some of the more complex operations which involve QKT and XV type kernels, we do have a method by which in the model factory you can annotate these custom operations. And then once it enters the compiler stack, the compiler can utilize kernels written to generate code at a low-level IR and integrate them in with the compiler, and the compiler can generate the eventual graph that gets lowered onto the chip. So in conclusion, just to end this, I mean, let me talk a little bit about the design philosophy behind this. So what you've seen is we've talked essentially about the kernels approach, which feeds into the model builder approach, but we've also talked a little bit about our hybrid approach, where we have a compiler which does a bit of automatic code gen, but also can integrate these kernels. And so we have this continuum of lowering options. The model builder and the kernels allow us to do aggressive operator fusion and move rapidly from various ops to kernels. And this has allowed us to build these kernels rapidly. We were able to build these kernels rapidly, use them for RTL validation, use them pre-tape out on emulation to check and make sure that we were able to deliver the performance we wanted to. And increasingly, we're using this approach to deploy models. It also allows us to validate our hardware, make sure that our hardware can achieve the performance that we expect it to achieve. Our second approach, our compiler approach, it's more towards a approach which frees the user from having to do these low-level details, allows us to extend our coverage to a wide range of ops, and to a certain degree is a little bit of a digression from the GPU world, where we're used to kernels and we're used to building these operations and then tying them together and fusion of these operations. The compiler does this more in an automated fashion, and thereby provides flexibility and op coverage. And something that we're increasingly looking at, which we haven't really talked about today, is using a CPU fallback, building a CPU fallback. And we have a proof of concept around this, where we would take a large workload, and then parts of the workload which are not implemented on our core, we would fall back to the CPU to do this, to do those operations. And we're prototyping this operation, this feature right now. And we're taking a look at it.
So is this like the private use, or like is effectively you're implementing like your own device basically within PyTorch, right?
That's correct. Yeah.
Okay, I see.
All right, and with that, I'll hand it over to my colleague Akhil, who will cover the runtime.
Thanks, Satyam. So Mark will switch screen shares.
Sounds good. I think you're muted, Akhil.
Yeah, just give me one. Sorry, maybe you can bring up the slides. Sorry.
It's not working. All right.
I have to restart my browser for this. Okay. Yeah. Thanks, Satyam. So we'll cover. We'll move on to the execution side of our stack and cover our inference engine and serving. Right. We've looked at the lowering side of our stack. So in inference, on the execution side, I'll primarily be covering our Aviator runtime, which is our host runtime, and our Aviator inference engine. So we'll start with the Aviator runtime. So Aviator runtime, the goals of this, we designed this to provide a model agnostic runtime layer for our accelerator, right? So the idea is to basically take in a compute graph, take in its input tensors, and execute that on our accelerator and provide the output of that graph to the user, right? So we operate at that level of abstraction with runtime. And so this allows us to basically minimize user friction when it comes to deployment. And one of the goals as we do this, like you saw so far, right? So we built the accelerator and our kernel stack to achieve extremely low latency and high throughput operation. So one of the goals of the runtime is to be able to serve that, right? So how we do this, right? How do we do this? We do this primarily with support for asynchronous graph execution throughout the execution stack. And so with that, and then for to minimize the user friction, right, we manage a lot of the host on-device memory management for activation tensors under the hood. We do any necessary type conversions, say from torch native numeric formats to dmatrix specific numeric formats, also under the hood, right? So now these are things that we have already available right now, and a roadmap item is to support dmatrix collectives through the runtime, right? So we have collectives through a different part of our execution stack, but we'll get there. Now, I want to go into a little bit about the foundations of the runtime, right? The first part of it is what we call DMX tensor. So DMX tensor is a tensor abstraction that that is used in the runtime to represent any tensor that is resident on the device, right? And it sort of plays matchmaker between the host side torch tensor and the device side tensor. So what you have in the code is sort of like the prototype of this DMX tensor. It essentially manages the device memory location, what is the size, the data type of this tensor, and also takes in a host tensor and keeps a deep copy of that. So DMX tensor, as part of it, supports the type conversions that I talked about. So it supports type conversions in two parts, two forms: explicit or implicit or lazy, right? When it is explicit, the user says explicitly that this tensor should be on the device and it should be of a certain data type. Now, what that means is that it will help hide any host to device data movement, so that you can, as soon as the tensor is created, you create it on the device and set up the data immediately. So you can hide host to device data movement. The implicit or lazy use case is to just allow programmer simplicity. So the user need not specify anything. Just based on the graph that is being executed, we do the type conversions under the hood. And another key foundation within the runtime is asynchronous graph execution. So how do we do this, right? So if you think about it, these are some of the key parts of our execution stack in blocks, right? So on the left side, you have our Aviator runtime and host memory, and on the right side, you have the device DDR and also the quad runtime that is running on the quad on each of the quads. And we create this structure, we dedicate a specific section of the DDR for what we call the job queue. Essentially, job queue is the location where the quad runtime is essentially looking for work at the job queue. So the host job is to publish as many jobs to the device as possible by writing things into this job queue, and the device's job is to execute as many jobs as possible by going through the job queue and figuring out what needs to be executed and executing that. Right. In practice, how this works is the runtime moves the inputs to device DDR, and it constructs the job queue as appropriate and writes the job queue entry. And then the quad runtime basically is waiting for work on the job queue, and it as soon as there is work to be done, it goes ahead and reads the job queue entry, understands it, and dispatches the work onto the computational units on the accelerator. And on the return path, right, so that was the forward path of execution. On the return path, right, the other foundation for asynchronous execution is a callback mechanism. So the runtime, when it knows that a job completed, it invokes a callback all the way to the host, and the host, upon receiving the callback, handles whatever needs to be done for that job based on the callback that it received, right? So, for example, read the output from the device. So this is how we achieve asynchronous graph execution. So with the runtime, a typical user flow would look something like this. So here you have on the right the user, Aviator runtime, and DMX tensor. So the user would initialize the runtime first on this part, and then the user, by the time user is trying to execute something with the runtime, there is already a lowered graph. So the user would load the graph and say, okay, for this graph, this is my callback function. And so user would load the graph here and receive a reference to that graph. And then for this graph, there will be how many ever inputs, and user would create DMX tensors for those inputs, right? And along with that, now the user is ready to call execute graph, asynchronous execute on that graph, right? So it provide the graph reference and the DMX tensors for the inputs, and user calls the execute graph in that manner. And finally, the graph execution happens on the device, and the callback that was registered gets executed when the job is done. So this is a typical user flow with executing through the runtime. Now making this a little bit more concrete. So this is how, for example, you would execute matrix multiplication through the runtime, right? So you just instantiate a runtime. Before I go into the details, actually, what my goal here is also to draw parallels, or maybe imperfect parallels, to the CUDA stack, so to speak, because what I've highlighted here is these dark boxes, which semantically achieve some of the things that are achieved in the CUDA stack through certain APIs, right? So the first part, what we're doing is a load graph. So what does load graph do? It takes a compiled graph and then registers that there is a callback for that compiled graph, and along with that, it moves the graph executable, the associated constants and weights from host to device, right? Host to device DDR. So all of this happens in the load graph. And when we next step after that is to prepare our inputs. So create an input tensor, create that as a DMX tensor, and along with now this basically allows doing this as by specifying DMX here, essentially moves the tensor, creates the tensor on the host, moves that tensor to the device, with the appropriate type conversion as indicated within this graph, right? Our necessary type conversions are indicated in the graph. And finally, we go to graph execution, where this graph now, we had two graphs that we loaded here, init graph and the execution graph. So we first execute the init graph. So what's happening in the init graph? Init graph is where we would do things that are necessary only once per model, right? So for example, this would be moving the weights and constant from our device DDR to on-chip SRAM, right? So that would be something that we do only once per model and execute many inferences through that through that model. So we place those things in the init graph, and that executes once. And following that is our execute graph, where we're doing the actual operation for a given activation, and we do that by calling this execute graph. Finally, after that is done, right, we wait for the callback, which releases this semaphore here, and that's how then we're ready to collect the outputs of our result. So this moving further, right now, then the component above our runtime is the inference engine. So our runtime was the model agnostic execution layer for graph execution. The inference engine is where actually we're building model-aware intelligence on the host side, right? So not only is this model-aware, we want to support multiple models, different types of models, and we want to support distributed inference, as we can see, right? All of our models, especially LLMs, we would expect it to work on up to a node or a rack or even beyond. So support multiple distributed inference. So the same goals of minimizing user friction and supporting low latency and high throughput operation apply here as well. Now, how do we achieve these goals, right? So again, inference engine is also built for asynchronous execution. It is built for tensor and pipeline parallel support. And to support our stringent performance requirements, we've been very conscious in minimizing host overhead as much as possible. And as many of you in the audience would know, a lot of this would come from inter-process communication and inter-process synchronization. So we minimize that as much as possible, or move that out of the critical path. And then that allows us to achieve this low latency, high throughput operation, right, together. So this is where what are the model aware features, right? For example, this is where we would implement things like continuous batching, paged attention, or prefix caching, prompt caching, so speculative decoding, so on and so forth. All of these are focused on LLMs, but for other models also, any model aware intelligence we would implement over here. Okay. So I'm going to get into a little bit about the inference engine architecture. So there is a lot here, but mainly there are three sections, right? First is our serving endpoint. So this is a thin, as I described this, I'm going to mainly focus on LLM serving, right? So a thin user-facing API server and an LLM that feeds into our LLM client. And following that, we quickly move on towards the inference cluster management, right? And on the inference cluster management, this is all I want to stress that this is all just the host view that I'm talking about, right? So we have the engine, right, and then we have a worker per each of the card that is involved in the inference, and then these workers are organized either depending on the model that needs to be deployed. Multiple workers form a tensor parallel unit or a TP unit, and then depending on the number of pipeline stages in the model, number of sets of workers will form the pipeline stages, right? So this is the whole distributed cluster management architecture. I'm going to go into a little bit of depth into each of these, especially the worker I'll reserve for a little bit for the later. So things to note: one worker per accelerator, pretty typical across distributed deployments across the accelerator space. And then the engine is where a bulk of the things necessary for serving, or the brains of the serving is happening. Okay, moving further. Now, let's look at the engine. Like I was mentioning, engine is the brain of the serving logic, right? And why do I say that? Because this is where most of the decisions happen. Most of the and this this is the also the performance critical piece, and we've co-designed the operation of the engine all the way up to the kernel, and maybe even up to the runtime, like you said, like we saw earlier, right? So, for example, things like how do we handle dynamic shapes, right? So, engine is the one that decides, okay, now I'm executing token decode iteration number X, and I need to, for a request Y, and therefore the KV cache for this request Y for this token iteration X is at a specific location Z, right, on SRAM. So engine is the one that communicates all of this to the graph, and then with the help of our quad runtime and how the kernel is written, we can execute, we can resolve dynamic shapes at runtime. And so as we're doing this, so engine is managing critical resources on the device. So KV cache resources, or to support pipeline parallelism, activation buffers across that for communication between pipe stages. And also it is the one that is executing the overarching LLM state machine. For example, which request is in prefill versus decode, which request, whether it needs to terminate or continue with auto regression, and also provide streaming back to the user, right? So this is the high level of what the engine accomplishes. Now, then we come to the workers, right? So the workers are designed to be very thin and lightweight. So engine is the one doing a lot of the logic of orchestration, and workers are essentially following the commands from the engine, right? So as we described earlier, right, host overhead, a big chunk of it comes from communication. So we have tried to be extremely efficient with communication. So essentially, what in our design, what we've accomplished is basically no worker-to-worker communication, right? Pretty much throughout the critical path, right? And also all the control communication for pipeline parallelism, right, happens outside of the critical path only at init time or to propagate errors, right? And finally, for like others have also mentioned, for collective communication for tensor parallelism, right? While it is on GPUs, it is host driven, right? Here, the host is not involved in collective communication. Collectives are baked into the compute graph, and the only host side inter-process communication is between engine and worker. So by doing this, we are able to add very little host overhead on a per token basis, right? So and we've also designed this with layering and separation of concerns in mind. So like I was saying, engine is the one. Our workload, we can define them in stages, right? Or we can call them as stages, like what Uttam was talking about. a prefill stage, a decode stage, and so on, right? So engine is the one that orchestrates the workload's execution through the different stages. And for a given stage, it calls on to a block called the stage runner that executes a given stage, right? And stage runner essentially interfaces with the runtime that you saw above, right? A stage can have multiple graphs, for example. So stage runner is going to go ahead and execute one graph at a time by calling on to the runtime. And runtime handles the lower level management of graph execution. So yeah, this is what I had about our execution stack. And going in, then I wanted to give a quick peek into research at D-Matrix. So research, we are also, while being a startup, we actively focus on research, and there is multiple groups that are working on different areas here. The ML team works, and the numerics team works on quantizations and model optimizations in that form. And there is a broader systems focus as well. And the hardware team also, does active research and publishes. And we have some of these publications here at ICML, DAC, MLSys, etc. And we have an upcoming IEEE micro paper that describes our Corsair architecture and the system level scale out in a lot more detail. So, yep, I think this is what we had. Is there any questions we can answer, Mark, from the stream or from you?
I was muted. Sorry about that. Yeah, I think Celia has been doing a very good job answering all the questions in chat. Thank you. Like, I really liked how comprehensive this was. Like, I think on my end, well, I mean, I sort of had like an obvious question, and which is for a lot of like hackers and researchers, at least that I work with, like if when I notice, like when I go to your website, there's like a form we need to click to get access. And so I'm wondering, for researchers that you've collaborated with, is there like a PCIe form factor that they can just plug into like a gaming PC? If people want to get access, like, there's sort of a lot of interesting builders in the server that I think would want to sort of play around with stuff and see how well it goes for them.
Yeah. So we do have plans for a developer cloud coming up in the next couple of months. At this point in time, I think we're working with a few select customers, and it's more sort of large scale deployments that we're looking at. But we do have a plan for a developer cloud to come up in a few months.
Okay, then I guess I have a feature request, which is that like it would be great if the developer cloud has access to like low level hardware counters. Otherwise, it's pretty much like impossible to do any interesting performance work. So, yeah, I'd love to try it out when it's ready.
Yeah. Awesome.
All right. Well, I think then there's a good time to call it. Uttam, Satyam, Akhil, and Gaurav, thank you so much for joining. I liked how comprehensive this was. Like, I think I want to also especially go back to the beginning session. Like I'm not as much of an expert. But thank you. I really appreciate your time, folks. And I'll see everyone next week. Thank you. Bye-bye.
Thank you.
Thank you.
Thank you. Bye.